So for the variational method, the foundation of this method is that we can always define the Hamiltonian, even if we can't solve it. We can define the Schrödinger equation. So for any system, we can write out the Hamiltonian. It may get really complicated if we have a lot of particles interacting with each other, but we can write it. Solving is a whole other story, but we can write H. And the problem is that when we have this eigenvalue equation, the Schrödinger equation, we often can't find, what are the wave functions that will actually satisfy this equation. And so let's specifically look at the ground state. Variational method works best for ground state, the lowest energy state of a system. And that is one of its limitations, is that it really only works well for ground state systems. So if we know a little bit about the system, we can make a guess. We can guess what this wave function is going to look like. Often we'll know some of the boundary conditions of the system, and we have a sense of what it should look like. And we create what we call our best guess a trial function. And we'll call that function, in this case, phi. All right? And so then the question is, what's the energy of the trial function? What energy do we get if we use the trial function? Well, we know how to find expectation values. So the expectation value of an energy is just we take the integral of not our real wave function. We don't know the real wave function of phi star, our trial function. Use the Hamiltonian operator, our energy operator, phi, and then integrate over all space. Now this trial function, because it's not necessarily a well-behaved wave function, we'll take this and we'll divide by the normalization constant. So the normalization of our integral. So this is just in case the trial function isn't normalized. So I guess what I'll say is this assures normalization. So if your trial function is already normalized and this integral on the bottom is just 1, right? It's not a problem. So that'll give you some energy, but you don't really know if that's a good energy, if it's close to what the real energy is. And so there is a principle called the variational principle that underlies this whole thing. We won't prove this. If you want to prove, they're out there, and you can work through it yourself, but we're not going to go through it in this class. The variational principle states that if we take this trial energy, I'll call it E trial, it will always be greater than or equal to I'll say the true energy. So the trial energy is always going to be larger than the true energy. And at the best, you can get them to be equal, but it's only equal if your trial function is equal to the true wave function. It's equal to the actual solution to the system. All right, and so that tells you, what this tells you is that if you can lower the energy, you did better, because you get closer to the true energy. So if you have some way of varying your trial function such that it lowers the energy that you calculate, you're getting closer to the actual result. You are doing better. And so what we do is we will set up this problem. What we generally do is that we'll pick a trial function that has some parameters inside of it. So pick phi with variable parameters. And what we'll do is change those parameters in order to minimize the energy. So change parameters to minimize the energy, and that means that we've got the closest we can get with the way we've set up the problem, at least, to the true wave function and true energies of the system. And so that's the basic idea behind the variational principle.